this is TyroScience, simplified science to make you smarter. There was a time when knowledge of astronomy was essential for survival. A slight misunderstanding can result in a tragic demise. The year was 1676, and most seafaring nations were fighting to establish their dominion over the oceans, especially France, Spain, Britain, and the Netherlands or Holland. In such a scenario, it was of vital importance that sailors should be aware of their positions at all times. Have you ever been on ocean sailing in a boat far away from the coast? It's hundreds and sometimes thousands of miles of similar sight, and without the use of technology, it is tough to tell where you are. In the 1600s, it was a nightmare to navigate. To know your position, you need to know the latitude and longitude. Latitude was comparatively easy to tell using the position and angle of pole star and/or of the sun, but longitude was pretty hard. To know that, you need to know the Greenwich Time. If you know when the sun was passing local noon and Greenwich Time, you can calculate the longitude. It is worth noting that this method required a clock that can accurately tell the time for months, which was not available in that period. And the movement of the ships made it worse. The next best thing is to find a way to adjust the clock regularly. The way to do that was to look up in the sky and find a celestial phenomenon that can be accurately timed. One such phenomenon was Jupiter's 4 moons, and they can be observed by a telescope. The most promising among those was Io. It had the largest number of ellipses with an orbital period of 1.77 days, and it crosses Jupiter's shadow in every orbit. A Danish astronomer called Ole Romer was assigned the task of making a table of predicted times of ellipses of Io for the sailors. While doing so, he discovered something strange. The period was not constant. It was shorter when Earth was near Jupiter and longer when it was moving away from it. So either there was something wrong with the orbit, or the notion that light travels instantaneously was wrong. He went with the latter reason and concluded that the light has a finite speed, just like the sound. He tried to calculate the speed of light, but couldn't accurately do so because solar system dimensions were not known at that time. It took a few more centuries to discover the speed of light accurately. There are many methods to do so, but the main principle is common in most ways. A light pulse is released towards a mirror and back, and the time was noted for that. After a large number of measurements using various methods, in 1975 the speed of light was determined to be precisely 299,792,458 meters per second in vacuum. This is not an approximation. This is exact and definite. And the reason why is it so is because we defined our units of measurement based on this number. A meter is defined as 1 by 299,792,458 of the distance traveled by light in vacuum in 1 second. You use meters to measure the speed of light, but the very definition of meter is dependent on the speed of light. This speed is denoted by the letter small c. It is the upper limit at which matter, energy, or any information travels to the conventional space. This speed is only attainable by the particles of zero mass like photons. Particles with non-zero mass can come close to 99.9%, but they can't touch the exact speed. So why is it so? What happens if you keep supplying energy to an object that can continuously increase its speed? For this, we have to awaken the famous E equals mc squared. According to laws of physics, once you reach close to the speed of light, all the energy will be converted to mass. Then you have to increase the energy until the point when both mass and energy reaches infinity. Well, that was about the things with mass. What about light? Is there a way it can go faster? Let's take an example. Suppose you're traveling on a train running at 100 km per hour. For someone standing on the ground, your speed is 100 km per hour. What if you start walking in the train towards the front side at 5 km per hour? Now your speed for the person on the ground is 105 km per hour. Let's apply that to light. If you're traveling in a spaceship at half the speed of light and you release a beam of light, will the speeds add up in the same way it did in train and become 1.5 times the c? Well, no. Due to another law of physics, you shall not add to the speed of light, and the speed can never exceed c. Regardless of the motion of source, which is your spaceship, or the inertial frame of reference, that is the place from which you measure the speed. It doesn't matter whether you're outside the spaceship standing stationary or inside it traveling at half the speed of light. The light will always travel at same speed. A lot of laws of physics start to break if something travels faster than light. Theoretically, it will go back in time. There was a buzz that neutrinos were found to be traveling faster than light, but that is under suspicion due to a possible measurement error. C is the upper limit, but that doesn't mean that light always travels at that speed. It can go slower, in a way, while traveling to the glass, water, diamond and other transparent materials. So does it mean that with all the technology, even if we manage to get close to the speed of light, we can only travel 40 to 60 light years in one lifetime in a universe which is billions of light years? Well, no, not at all. The theory of special relativity again does something special. When something travels really fast or close to the speed of light, it experiences time differently due to time dilation. Suppose you are traveling in a spaceship that is going close to the speed of light. The time you experience will be different from what someone is experiencing at the Earth. You will only feel like 40 years older, but on Earth it has been thousands of years. And during that time, instead of 40 light years, you would have traveled thousands of light years. And when you come back, in a way, you would have time traveled thousands of years in future. It's fascinating how a simple quest to locate ships in the sea transformed our understanding of the universe and how light works. And despite its unimaginable speed, it is still nothing in the vastness of cosmos. But wait, what about Ole Romer? Did his method work? Well, as it turns out, observing Io from a telescope in a moving ship is not an easy task. If you have ever used a telescope, you know what I mean. Also, you need cloud-free skies, though it works for boats, islands, capes and other places on land. Sailors had to wait for a few more years for the exact location until more sophisticated clocks were invented. Do hit the subscribe button if you like this video. Let me know what topics do you want to see next. And as always, keep learning, keep exploring until you know everything.